In this lesson, you're going to learn how to integrate trig identities like this one. And by the end of this lesson, you'll be able to do a question like this. So stay tuned. So in this lesson, we are going to be looking at integrating the trig identities. So before we do that, just to recap, these are some of the trig identities that we have. We have sine squared theta plus cos squared theta is equal to 1, sec squared theta is equal to 1 plus tan squared theta, cosx squared theta is equal to 1 plus cot squared theta. And then we have the double angles that we've done in previous chapters. So we have sine 2 theta or sine 2x is equal to 2 sine theta cos theta. We have the cos 2 theta, which is equal to 3 different identities there, and we can use any one of those 3. And of course we have the tan as well, which we won't really be using much here because we have tan actually integrating to a specific thing which we've seen from previous examples. So if you want to make a note of these diagrams, please. One thing we are going to do is see where we have the cos 2 theta and the sine 2 theta. We are going to be getting used to rearranging these for other terms. So for example, we can rearrange 2 cos squared theta minus 1 to make cos squared theta the subject, all right, giving us this, okay? But I'll show you this through examples, okay? Or we can rearrange sine squared theta and we can have sine squared theta is equal to a half minus a half cos 2 theta. All right, so let's start off with the integration of these two and then we'll look at a couple more, okay? And we'll finish off with a definite integration by the end of it, all right? So have a look at this. So cot squared x, we want to differentiate, we want to integrate this. So what do? Do we know a substitution for cot of x? For cot squared x is we can use that identity that we have. We know that cosec squared theta is equal to 1 plus cot squared theta. And what we can do now is make this the subject. Okay, we can rearrange this and make that the subject. So to make this the subject, what do? We take the 1 to the other side and we have cot squared theta is equal to cosec squared theta minus 1. And what we can now do is say, rather than looking at this and integrating, we can say, let's integrate cosec squared theta minus 1 dx. Right? And we know that something, if we were to consider, what differentiates to give us that cosec? What differentiate to give us cosec? Well, cot, if we were to look at cot theta, we saw yesterday, or we saw in the previous lesson, that when you differentiate cot, what do you get? You can look back at that, that table that you have. What do you get? Minus cosec squared theta. Right? So when we differentiate cot theta, we get minus cosec squared theta. And then we just have to compare what we have and what it differentiates to. So we have this negative here that we don't want here. So we have to divide this by a negative. So therefore, the integration of this would be a negative cot. So it will be minus cot theta. And then we have to integrate this, which is going to be minus x, and then we have the plus c. So this is this one's integration. All right, so let's get rid of this now. Let's have a look at cos squared x. So cos squared x, we know that it's related to cos 2x. Now some of you may be wondering, and you're thinking, hold on a minute, why can't we consider y is equal to, what would I normally consider with this power? No, don't go there yet. We can do 1 minus sine squared x, but if we have 1 minus sine squared x, then we still got the same problem of this square, sine squared x, yeah? But is anyone out here thinking, you know what, why don't you consider cos cubed x, for example? Yeah, and then when you differentiate this, we have 3 cos squared x, and then what do we have to have here? Because we have to differentiate this now, it's a chain rule. Minus sine, so we'll just put the minus sine x, right? But the issue that we have here is we've got all of this, right? And if we were to do the integration of this, for this, the problem is that, or we were to compare, okay, you might say, well, get rid of it by doing divide by minus 3 here, and get rid of it by dividing by sin x. But we can't divide, we can only divide, or we can only manipulate or adjust by constants and not variables. Sin x is a variable. Okay, so that's because sin x is there, we can't say, oh, we will divide by minus 3 and sin x. Do you understand this? Yeah, so you can only divide by constants, okay, negative signs or a number, okay? So that's why we won't consider this. So for cos squared x, we can consider our double angle for this. So what does cos 2x equal? That uses this. 2 cos squared x minus 1. And we now can rearrange this to make this the subject, right? So what do? We take the minus 1 to this side. So what do we get? Cos 2x plus 1 is equal to 2 cos squared x. And then we divide by 2. So you get half cos 2x plus a half is equal to cos squared x. And this is what we can integrate. Okay, so let's rewrite this. So half cos 2x plus a half dx. Look at this one. So what we will consider is what differentiates to give us cos? Sine, right? So we'll consider sine 2x. So dy over dx is equal to what? 2 cos 2x. And now we will look at this and look at what we have here. So we don't want a 2 there, do we? So we're going to do what? We're going to divide by 2. But we do want a half. So we have to divide by 2 again. What's the process going to be now? To divide by 4. So it's going to be this, our integration. So it's going to be a quarter sine 2x. So the integration of this is a quarter sine 2x. So now we go to this plus. What does that give us? We increase the power. So it just gives us a half x plus c. So onto these two. Let's have a look at this one first. We've got sine 4x and cos 4x. Does that remind you of anything? Does it remind you of any of the double angle? Which one? Write it down. So it reminds you of sine 2x, doesn't it? Which is 2 sine x cos x, right? But we are dealing with whether x is 4x. Now, what relationship is there between this and here? What relationships? The angle here and this. It's half or double, yeah, whichever way you look at it, right? So if we're looking at 4x's, we're going to have 2 sine 4x and cos 4x. What do you think this is going to be? 8x. Very good. It's going to be 8x, yeah? So what we are going to do now is to rearrange this so we have that, just like that. So how do I do this? And to get rid of the 2. So what will I have now? A half sine 8x is equal to sine 4x cos 4x. So what will I be integrating? I will be integrating this. Okay, so let's go and integrate. So instead of this, we'll be writing that. And we will consider what? What should we consider for this one? What does this differentiate from? Cos. I know, don't worry about the minus for now. Yeah, we'll just leave that out for now. But we know that you get a sine from cos, right? So we'll write cos 8x as our consideration. Now, I know that when you differentiate this, we know that it gives you a minus 8 sine 8x. Isn't that so? Yeah? So, let's manipulate this. We don't want a minus because this doesn't have a minus. We don't want an 8. So, the first thing we're going to do is divide by minus 8. But because we also need a half in there, that's right, you got it. We're going to have a total overall of minus 16. So, our integration for this is going to be this, but with a minus 1 over 16 cos 8x plus c. All right, very good question. Question, why this minus 16? So I'm just going to repeat that. We have an 8 here. So if you forget the half on our original, right, we don't want that 8 there. So we're going to divide by 8, right? But we do want to have a half. So how do we get a half overall? Well, if we wanted a half, normally we'd just divide by 2. But because we're dividing by 8 as well, the 2 and the 8 will multiply on the denominator, giving you 16. So overall, you have a division by 16. And that's why it's 1 over 16 times that. Okay? They're good? Perfect. Perfect. All right, so now have a look at this one. Secx plus tanx squared. What's your first step? Expand. Very good. We can expand that. So we'll do that over here. So what do you get when you expand this? You have double brackets. So you have sec squared x plus secx tan x. And we have how many of those? 2 of those. So we'll write 2 sec x tan x plus tan squared x. So this is what we are going to integrate. So let's look at sec squared x. We know that it comes from, we've done it earlier, tan. It comes from tan, right? So we can consider, let's just quickly do it one more time. So we can consider tan x. We know that when you differentiate tan x, we've seen from the previous chapter that it gives you sec squared x, right? So this is exactly as we want it. So the integration of that is going to be tan x. Moving on to this one. What does this remind you of? What does it come from? Sec tan. We have, what can we consider from sec tan? Sec itself, right? So let's do that up there. So we can consider y is equal to sec squared x, right? So when you do this, you do dy over dx using your chain rule. Pull that 2 down. What do you get? Sec x, and then differentiation of sec is tan. Yeah? So you get 2 sec tan x. Exactly what you want, right? So therefore, what's the integration of this going to be? Plus sec squared x. So for tan squared x, we know that tan squared x is equal to sec squared x minus 1. So we can integrate this. Yeah? So let's just do the integration here, and then we'll just put it here, the result. So what's the integration of this? What do we get? We've seen that from up here. We get tan x. So we get tan x. And this is going to be minus x. So let's put that in here. We get tan x minus x. And we have our plus c. Now here, we've got tan x here. We've got tan x here. We can put them together. So overall, we have 2 tan x plus sec squared x minus x plus c. And that's our answer. On to the final question. So we're building up towards questions like this. What's this linked to? It's linked to cos 2x. And what is the identity for that? 1 minus 2 sine squared x. However, just like before, the angle here, and this is doubled, right? We are dealing with 3x. So therefore, if we are dealing with 3x, we're going to have 1 minus 2 sine squared 3x. Meaning, this will be double the 3, right? So it's going to be 6x. And we are going to make this the subject by taking all of this over to the other side, taking this to this side, and then dividing by 2, right? So that will be sine squared 3x is equal to 1 minus cos 6x, and then we are going to do the division by 2. So therefore, it's going to be 1 over 2 here and 1 over 2 there as well. It's a bit squashy. Just write it nicely. They're good? So we are going to integrate this. So let's write this down here. So we are going to be integrating between pi over 3 and pi over 6, a half minus a half cos 6x with respect to x. And when we integrate between limits, we will use our square brackets. So what's the integration of that, please? It's going to be a half x. For this, we'll do some considerations. So let's do that here. So consider. So where does cos differentiate from? What will we be considering? sine 6x. So dy over dx will be 6 first, yeah? So 6 cos 6x. So if we look at what we have and what we have here, we make that adjustment. So we want to get rid of the 6, all right? Now this sign minus is part of the integration, so we can just put that there. So we're going to divide by 6, and we're also going to have that half in there. So overall, what's that going to mean? A division by 12. So we're going to have 1 over 12 and sine 6x. And we are integrating between those limits. When we integrate between limits, we sub in the higher value for our x's, sub in the lower value for our x's, do the higher version, take away the lower version, yeah? Right? So I'm just going to get rid of all this. So working up here. So let's plug it in. So I'm going to do this in 2 steps. I'm going to have half times pi over 3, close brackets, minus 1 over 12 sine bracket 6 times pi over 3, close that bracket. That's my first substitution done. Next, I'm going to be taking away, again this time, half times pi over 6 minus 1 over 12 sine bracket 6 times pi over 6, and that's my second bracket done. Let's tidy up a little bit here. So what do we get from here? We get pi over 6. Now tidy up this one, so minus 1 over 12 sine, so 6 over 3 is 2 pi. That's the first bracket tidied up. Minus, here, what do we get? Pi over 12 minus 1 over 12 sine, and what do we get here? The 6 is cancelled, so it's just sine pi. Now you're probably reaching for your calculators already, but you can actually do this without a calculator. And usually a question like this might even say, you know, show or give exact values. So if you put that in your calculator, you may not get exact values, you might get a decimal. All right? So I just want to quickly show you how you can do this without a calculator. Now to do this, consider the sine graph. Have a look at the sine graph. So I'm just going to draw the sine graph here. And the sine graph, we know, is looking like that. And this is pi, and this is 2 pi. Now at the values of pi and 2 pi, the values of sine are what? 0. So 2 pi is 0, so 0 times by this, all of that is 0. So you just end up in this bracket with pi over 6. And the same, sine pi is also 0, so therefore that goes, ending up with minus pi over 12. So minus pi over 12. And that's all you have to work out. Right? Now, you might, just a quick reminder, if you just forget about the pi's, if you look at 1 over 6 minus 1 over 12, convert this into a same denominator, so you get 2 over 12 minus 1 over 12. What's the answer to 2 over 12 minus 1 over 12? 1 over 12. So what's the answer to this going to be? Pi over 12. And that's your exact answer to this. So a question might say, show that this equals pi over 12. And you'll have to do all of this working to get there. Hope you enjoyed that lesson, and I'll see you in the next one. Bye for now.